Good morning, everyone. How's it going today? In today's video, we're going to be covering a different kind of video, actually. We're going to be doing an overview of this new article that was published by Anthropic recently, titled How We Built Our Multi-Agent Research System. And we're going to be summarizing the entire article right here for you so that you learn a little bit more about how to build multi-agent systems. So we're going to be going over all of that. And this article covers four main parts. The first one is the benefits of a multi-agent system. After that, we're going to be covering right here the architecture overview. And so we're going to be going over exactly how they organize the architecture. We're also going to be covering a little bit about the effective evaluation of agents, how to evaluate agents and when to evaluate the agents, and also a little bit on the production reliability and engineering challenges of deploying agents. And very importantly as well, before I forget, this is probably the most important part of the entire video, the prompting advice that they give us for prompting multi-agent systems. Incredibly, incredibly useful. Okay, so let's get right into it. So let's start with this. The first thing to keep in mind is the benefits of a multi-agent system. And this is something to consider because not every task requires an agentic system, and not every agentic task requires a multi-agent system or is compatible with a multi-agent system. So essentially, we have three different types of tasks within AI tasks. We have regular AI tasks, which can be done with a single one-shot request to your AI model. You have agentic tasks, and within the agentic tasks, you have the single agent, and multi-agent. Okay, so that is what we have right here. And what Anthropic guys found is that research is one of the latter multi-agent research tasks. But why do they need a multi-agent system in this particular case? And the reason for that is that this kind of task, such as research, works very well with parallelization, right? Now, what does this mean? This means that what they did is they built a system where they have a lead orchestrator with Opus 4. So this is going to be the lead orchestrator. And then below him, they had several Sonnet 4 agents like this. And each Sonnet 4 agent was in charge of one task that Opus 4 assigned to them. So this orchestrator right here would decide how many sub-agents it needed to create, to delegate those tasks to. So for example, if for some simple research, the master agent decided that he needed 3 sub-agents, he he invoked those 3 sub-agents into existence, gave them tasks to complete, and then those sub-agents would complete those tasks, right? And this kind of pattern works very well with a research approach where you can have multiple researchers performing research on different individual aspects or individual topics of your overall topic, and then you can put everything back together by the end. You can have the orchestrator put everything together, all the research by these other 4 guys or 3 guys, and put it back together as a whole, right? But for example, it would probably not work very well with coding, right? So in coding, it's different because in research, you do not necessarily need all that context in real time of what the other guys are doing, right? So this guy can perform his own research, get back right here, and then this guy just puts everything together. In coding, on the other hand, this guy kind of needs to have a very clear idea of what the other guys are doing in real time to actually make sure that they're not breaking things. So for now, coding remains a task where a single agent works better, whereas research works better in a multi-agent system, right? And that is exactly what they say right here. Let me just find it. They say some domains that require all agents to share the same context or involve many dependencies between agents are not a good fit for multi-agent systems today. For instance, most coding tasks involve fewer truly parallelizable tasks than research, and LLM agents are not yet great at coordinating and delegating to other agents in real time. And something else that I found very, very incredible about this is that they say that this system right here, having the multi-agent system where one guy is the orchestrator and he delegates the activities to several Sonnet 4 models, they say, we found that a multi-agent system with Claude Opus 4 as the lead agent and Claude Sonnet 4 sub-agents outperformed single-agent Claude Opus 4 by 90.2% on our internal research eval. That to me is incredible. That means that if you have one task and it is very, very sophisticated task, and you have an Opus 4 model, which is the largest model, think about that problem, then solve the first task. That would be Opus 4 again. Then you solve the other task with Opus 4, and all the way only Opus 4 one time after another. This, what you get from this guy right here, will be worse than if you had your Opus 4 delegate to Sonnet 4, which are inferior models or smaller models. And this right here, having O4 delegate to multiple Sonnet 4, will have a way better result than having Opus 4 do everything by itself. And I just find it very incredible. And the reason for that is actually mentioned right here, right? We found that token usage by itself explains 80% of the variance, with the number of tool calls and model choice as the two other explanatory factors. What does this mean? It means essentially that the more tokens that you use to solve a task, the better the results of that task. So the quality of the result of your task is mostly dependent of these three parameters: the number of tokens that you used to solve it. Secondly, the number of tools available, or tool calls available to your agents, and then the model, of course. But of this, the most important one is the number of tokens. And when you see that, actually makes sense that this configuration right here will work better than this one right here. Because in this one, you will necessarily use more tokens because you're initializing multiple agents with very specific tasks one at a time, right? Whereas here, you have the same guy keep the context of everything at the same time, and that reduces the total number of tokens. So this one right here, 90.2% better than the other one right here. So very, very interesting. Now let's take a look at the architecture of how they build this. The architecture right here is actually a very interesting approach. So on the left, you have your client, which is your Claude AI chat or whichever interface you're using to communicate with this multi-agent system. And on the right, you have the actual multi-agent research system. And as you can see, you have one lead agent orchestrator. Let me just show this to you right here. You have the lead agent orchestrator, which has access to tools, to MCP tools, to memory, and it has, very importantly, let me show this right here, access to these two guys right here, the run sub-agent tool and the complete task tool. And this is the guy who is going to be using run sub-agent tool to create multiple sub-agents and give them the goal or the prompt that they need to actually complete their task. Also, very importantly, this guy also has access to memory to save the initial plan. And then they also created a citation sub-agent that will make sure that everything that the sub-agents bring to the table actually is backed up by actual research, by actual sources from the internet. And here's an actually more detailed diagram of what is going on. So it all starts with the user. The user will send a user query like this right here to the system, and we will start the iterative process of the multi-agent system. So the first step right here is to start by creating the lead researcher, which, if you remember correctly, works on Opus 4. Do not confuse this with O4. And it starts by thinking. Very important step. It will think about the plan that it needs for the entire research. So these are the research topics that I need to focus on, and it will store that plan in memory, as you can see right here. Okay, so it will store that plan in memory, and then it will retrieve that context whenever it needs to, right? Remember that at some point during the entire process, this guy may run out of context. So you will have to squeeze the context back by summarizing it or by putting it at a different place, but you cannot lose that initial plan that you started with. So that's why they implemented this memory system right here. And then once it has defined all of the steps that it has to complete in order to complete the research task, it is going to initialize as many sub-agents as it needs. In this example, we have 2 sub-agents. So it will initialize the sub-agent 2, And each sub-agent is going to start thinking and evaluating whatever it thought about and find an actual response to whatever its very specific topic of research was. And then once they finish off their research, they will come back to the research agent, and this guy is going to think again, make sure that everything makes sense, synthesize all the results, and then just bring those back to the system. In the system, as we can see, they also added this extra step with this citation agent, who is going to make sure that everything makes sense and that everything is backed up by the process documents, the research report, and with the citations to make sure that everything is actually backed up by something in the internet, right? So that's the architecture. I think it's very, very interesting. And actually, this makes me think a little bit of, I don't know if you remember the Storm paper on creating Wikipedia-like articles using language models. Let me see if I can fetch it for you right here. So here it is, I found it. This paper is a paper titled Assisting Writing Wikipedia-like Articles from Scratch with Large Language Models. And it was published, I think, last year or the year before that, 2024. And the idea behind this one is that it created this system that allowed you to do a lot of very detailed research. It mimics a lot what we are currently seeing in the article by Anthropic. But something that I found very interesting about this other paper is this right here. Let me just erase my scratches right here. Contrary to what the guys at Anthropic did, where you have each individual researcher think and reason about their individual task, these guys right here actually have two agents by sub-agent, okay? So in the Anthropic's system, you would be a single sub-agent researching the web using research tools, etc. In this case, they have a couple of agents. One was the actual expert, and the other one was the researcher, or the equivalent of the current sub-agent. And what happened is that this guy would ask a question to this other guy. Now, this guy was the one who had access to the tools from the internet, etc., and he would ask the questions from this guy. So what turned out from this is that this conversational approach of this guy who knows what he's talking about, so he knows what questions to ask, and this guy has access to the research tools, what happened is that this turned out to return way better results than just having one guy try to be curious about everything and figure out what it has to look for, and then performing that research and getting the results back. So mimicking that conversational aspect of it turned out to be very, very beneficial. And I wonder if they actually do this behind the scenes in Anthropic and they just did not mention it, or maybe they just don't apply it. In any case, I think that this would be an interesting thing to try if you're trying to replicate these kind of things. So let's go back to the paper right here and let's talk about the prompt engineering part. So here's the part where it all becomes a little bit more interesting. And the reason for it is that we have actually very clear advice on how to create better prompts for our multi-agent systems. And here they have a series of recommendations. So the first one that they give us is think like your agents. And essentially what they say right here is that they just watch their agents work step by step from the beginning to figure out what they were doing, okay? So I feel like this recommendation right here just boils down to installing a very clear observability platform from the beginning of the development process to figure out what is actually going on behind the scenes, and so that you can actually create effective prompting. As they say, effective prompting relies on developing an accurate mental model of the agent, which can make the most impactful changes. So second part right here, and I think that this one is probably the most important part in the prompting advice that we're getting, is teach the orchestrator how to delegate, okay? So we see right here that each sub-agent needs an objective and output format, guidance, and the tools and sources to use, and clear task boundaries. Now, this of course is very clear to us, but it is not as clear to the orchestrator if we do not tell it to him. So this thing, we have to add it to the prompt to our orchestrator so that it knows how to invoke new sub-agents. Second thing right here is that agents actually apparently have quite a difficult time at figuring out if a task is difficult or not, and how many agents they need if they are not prompted specifically to figure that out. So apparently the guys at Anthropic found that at the beginning, when they were not prompting for this, the orchestrator was spawning like 50 agents for a very simple task, a very simple research task. And that, of course, does not make sense. So what they did to fix that is that they added this little rule to their prompt saying that simple fact-finding queries must use one agent with about 3 to 10 tool calls. Then direct comparisons might need 2 to 4 sub-agents with 10 to 15 tool calls each, and complex research might use more than 10 sub-agents with clearly divided responsibilities, right? So if you ask something very simple to Claude, it is not going to try to spawn 50 different sub-agents to solve your question. And this is something that had to be prompted directly to the orchestrator so that he knows how he has to handle these kind of things, right? And then after right here, we have tool design and selection. And if you have ever built an agent, you probably know that it is not very straightforward. And figuring out how to create tools is not very straightforward, and how to write the description for them is not straightforward either. And here they say that it is very useful to prompt the agent so that before it actually does anything, it looks at the tools and figures out if any tool is useful to whatever they need to do, instead of just trying to make it figure out what the tools that it's going to use are going to be more useful. Okay, so here they say, for example, examine all available tools first, match tool usage to user intent, search the web for broad external application, or prefer specialized tools over generic ones. And this is something that you have to write in the prompt, because otherwise the agent is just going to try to pick whatever tool it can find, apparently. So you have to very specifically tell it to choose the best tool for the job and to associate it to the task that it needs to complete. And also, very importantly, the tool descriptions have to be written very, very clearly. And in case you're not familiar with that, when you create a tool for an agent, you're essentially just writing a Python function, right? But the agent does not see the code itself. The agent sees a description that you write, that you add to your function. So you may have your function that looks something like this. So def, my function is right here, blah, blah, blah. And here you have all your code. But your agent is not going to see the code itself. The agent is going to see the description that you add right here in a doc string. And this description right here is very tricky to get it right, because you have a tendency to want to write that description as a documentation for your function. So you would write something like, get the latest items in a to-do list, for example, right? Well, that is not what you would write to an agent in a tool description. In a tool description, you would have to phrase it something like, use this tool to retrieve the latest items in the to-do list of the user, all right? So that difference in wording goes a long way. And that is something related to what they are talking about right here. Also, they mention, let agents improve themselves. And this is a very interesting thing that I noticed. I don't think I had seen this approach before, but they say that we even created a tool testing agent, which given a flawed MCP tool, it attempts to use the tool and then rewrites the tool description to avoid failures. So it rewrites the description. Of course, it will do this with another tool called update tool description, but I feel that this is a very interesting approach. And apparently, they found that this process for improving tool ergonomics resulted in a 40% increase in task completion time for future agents using the new description, because they were able to avoid most mistakes. Very interesting advice right here. We also have this piece of advice right here saying, start wide, then narrow down. Of course, this is something that you would want to add to your prompt. I mean, just to be clear, everything that I am mentioning right here are things that you want to include in your prompt that you're adding to your agent, right? So it says right here that agents often default to overly long specific queries that return few results, and that probably is a problem. So they counter this by prompting the agents specifically to start with short, broad queries and evaluate what's available, and then progressively narrow focus. Again, this is something that they added to the prompt itself to make it work. And this part right here is also pretty useful, pretty interesting. They added thinking to their agents. So thinking, in case you're not familiar with it, it is that first stream of tokens that comes before the actual answer from the agent or from the language model. So in the language model, which with reasoning capabilities will start a thinking mode, it will output thinking tokens, and it may output them for a long time. And then once it finishes thinking, it will then output the result tokens, okay? So essentially it's just like a longer answer, but you only see the last part. And this actually turns out to be very, very useful in creating agents and making sure that they understand correctly the query or the tasks that you're giving to them. And they added this thinking part to two different aspects of the thinking process or the task resolution process. The first part was they used extended thinking mode in Claude Opus 4 to output additional tokens in the lead agent, okay? So this guy uses thinking to plan its approach, assessing which tools fit the task, determining query complexity and sub-agent count, and defining each sub-agent role. Our testing showed that extended thinking improved instruction following, reasoning, and efficiency. So essentially, this means that using this thinking thing right here before having the agent write the actual plan of the entire thing, because remember that we have the agent, we have the lead researcher, first of all, create a plan of whatever it's going to do right here at the beginning. This plan is a result of a thinking part right here. And very interesting right here, you have also a thinking spot right here in each of the sub-A. And this is what they mention right here. So they mentioned that they use interleaved thinking after tool results to evaluate query, identifying gaps, and refine their next query. Now, interleaved thinking is a fancy way of saying just thinking in between tool calls, right? So what's happening right here is that we're kind of going back to a more articulated version of the React prompting pattern. If you remember correctly, the React prompting pattern is a thing that came out about a couple of years ago, probably. And it is a way to prompt large language models to make them understand what they have to do, to make them follow an instruction and enter this loop where they reason about what they're going to do. So React actually comes from reason, action, and observation. And what's happening is that when you send the query to your system like this, it will enter a reasoning stage and it will think about the query and it will know about the tools that it has available, right? So it will start thinking, okay, so the user wants me to do this. Probably they want to figure out if they have any meetings recently. So I am going to call the tool that checks the calendar, right? So they're going to call that tool. And then the calendar is going to return an observation, which is the result value of whatever your function returned, which might be the events in the user's calendar. And then it goes back to a reasoning step where it starts thinking, okay, so now I have the next events in the calendar of my user. Now I can decide, now I can tell him if there are any new events coming, and then you have an answer, right? So this is all a prompting technique, okay? And it was popularized a while ago. Now let me see if I can find it right here for you. Here it is. This is the paper that I was talking to you about, the React paper. It's a paper, I think, from 2023, apparently. And this one is exactly what I showed you before. It says, a unique feature of human intelligence is the ability to seamlessly combine task-related actions with verbal reasoning or inner speech, okay? So they're trying to replicate that inner speech with this token stream of thinking. And this was a thing mostly before, because they would fake this thinking loop in the prompt. This would not be hard-coded or in any case represented with a graph. It would just be the part of the prompt, and then you would continue like that. So I find it very interesting to see that the guys at Anthropic are kind of using this same approach right here, but with more controlled workflows. Now I will leave that paper and the other ones that I just mentioned in the description in case you want to take a look at those. But there you go. Now let's take a look at the next advice that we have right here, which is that parallel tool calling transforms speed and performance. And this is essentially just a fancy way of saying that when they spin up an agent right here like this, each one of these guys is actually executing the code in parallel, right? So this guy will create a plan. It will say, okay, so I need 3 sub-agents to perform my actions. Then each one of these sub-agents is going to perform their own research at the same time, okay? So this is happening in parallel. And they also mentioned that they added a little bit more parallelization right here with tools. So each one of these guys is going to complete the tool calls in parallel as well, okay? And so, of course, that is going to help with the speed and the performance of our multi-agent system, okay? So there you go. Now let's talk about, so that was prompting. And just to conclude on the prompting part, I think that this phrase is very interesting. Our prompting strategy focuses on instilling good heuristics rather than rigid rules. And I think that is completely right and something that you should very much be aware of when building multi-agent systems or any agentic system for that matter. Your prompting has to be based in heuristics, which means that it has to prompt your agent to be flexible and to adapt to any new information that might come its way. Because when you're building agents, the main aspect of an agent is that it has to be able to decide what to do given the results of its tools, right? So if you give it very hard-coded rules or very rigid rules, it will just have problem following them because your rules are never going to account for all the possibilities that the tool calls might return. So there you go, just keep that in mind. Now let's take a look at the effective evaluation that they used for their system. And as you may know, evaluating agents is never an easy task because agents are by definition black box, so you don't really know what's going on. I mean, you can know what's going on in the reasoning step, but language models are a black box. So a system of multiple black boxes interacting with each other and sometimes in a loop is just a pain. So it will be very, very difficult to evaluate how this works. However, that is what these guys are doing. So they say, because we don't always know what the rigid steps are that an agent will take, usually we can just check if agents follow the correct steps we prescribed in advance. Instead, we need flexible evaluation tools or methods that judge whether agents achieved the right outcomes while also following reasonable processes. So there you go. I mean, of course, this makes sense. Evaluation is a very tough thing to do, but here's some advice on how to perform valid evaluation for your agents. And the first piece of advice that they give us is that you should start your evaluation early on in the development process. So they say in early agent development, changes tend to have dramatic impacts because there is abundant low-hanging fruit. Prompt tweak might boost success rates from 30% to 80% at the beginning. So that is very, very important. And they also mentioned one example that they did. They said that they started with a set of about 20 queries representing real usage patterns, and they tested these queries to see how the impact changes in those small, even in those small changes, right? And this from the beginning. And they also mentioned that this is in contrast with common belief in the ecosystem that says that you have to have large evals with hundreds of test cases for it to be useful. Well, apparently you can do this with a more simple approach with a simple list of short prompts at the beginning to make it work, improve by a lot your system, okay? And second thing, I'm very happy to see this thing right here, which is the paradigm of LLM as a judge. And in case you're not familiar with LLM as a judge, let me just explain what it is to you real quick. LLM as a judge essentially just means that whenever you have a language model doing anything in your process, so you may have your language model right here, and you have your process right here. This might be your user, or this might be another part of your process that requires the language model, right? This part of your system will send a request to your language model, and your language model will send you the response. In this case, it can be one of the sub-agents who is the researcher, right? And what they did is they added an LLM as a judge paradigm. And the way that this guy works is that you have another language model right here in the middle who is going to intercept the response from the language model. It is going to judge it to define if it was a good response or a bad response. And if it was a bad response or not good enough, it will send it back with some feedback. And then this guy will think again and then send it back. And then once it is the correct response, only then will it arrive to the user or the final destination of that task. And that's exactly what they did right here. Let me just mention this right here. So they tested apparently multiple approaches to this. They said that they tested with multiple judges to evaluate each component, but found that a single LLM call with a single prompt outputting scores from 0 to 1 and pass-fail grade was the most consistent and aligned with human judgments, okay? This method was especially effective when the eval test cases did have a clear answer, and we could use the LLM as a judge to simply check if the answer was either correct and etc., right? Correct, okay? If the answer was correct. They did this by defining a very clear set of, like a grid of things that it had to evaluate from 0 to 1, right? So it would evaluate things like factual accuracy. So is this information correct? Citation accuracy. So do the cited resources match the claims? The completeness. So are all the required aspects from the task covered? Are the sources correct? Were the tools used reasonably, etc.? So all these kind of things are the things that this language model, who is the judge right here, is going to grade from 0 to 1. And then only if it gets a passing grade in every one of those aspects will the response go to the orchestrator, okay, in this case, or to the final user if that was where the judge was positioned. Then last but not least, we have that human evaluation is very important as well, apparently, because you cannot rely only on a judge or a language model to figure out if everything makes sense. And that, of course, makes sense to us because people, when testing agents, we can find edge cases that language models miss because language models are very straightforward. They will do exactly what we tell it to do, but they will not identify those little mistakes, little things that might be obvious to us. And they do give us an example. They say that in our case, human testers noticed that our early agents consistently chose optimized content farms over authoritative but less highly ranked sources like academic PDFs or personal blogs. So what they did is they added this source quality heuristics. I mean, they just added the prompt saying that whenever you find a source, identify if it is just an SEO optimized content farm or if it's a highly ranked source like an academic PDF or a personal blog, and privilege using those from academic PDFs and personal blogs over SEO optimized. So adding that to the prompt was what they did to actually fix this. And there you go. And then just a very quick reminder of what we mentioned before with prompting as well, saying that therefore the best prompts for these agents are not just strict instructions, but frameworks for collaboration that define the division of labor, problem solving approaches, and effort budgets. And actually, they invite you to check out their open source prompts in their cookbook. So actually, I'll leave a link in the description to this one right here, because they actually will give you the actual examples of the prompts that they are using so that you can actually see them in action. So I'll put a link of this one in the description if you want to check it out. And then last but not least, we have the production part. And they have some very interesting things to share with us right here. They say that agents are even harder to build than regular software. I mean, regular software is already pretty hard, but agents apparently are harder. Because just like with software, right? But in this case, it is even more dangerous and more problematic when we have an error. Because when you have an error in between, like in one of the thinking processes, right? You have multiple agents working at the same time. You have an orchestrator trying to orchestrate a whole thing. You have multiple sub agents trying to research different things at the same time. So if you are going to do that, you're going to probably have a hard time if at some point you have an error down to like 10 minutes in or 15 minutes in your reasoning and the process. You cannot just restart the whole thing, as they say right here. When an error occurs, we can't just restart from the beginning. Restarts are expensive and frustrating for users. Instead, we build systems that can resume for where the agent was when the errors occurred. And that, of course, makes a lot of sense. They also say that debugging benefits from new approaches. And what does this mean? This essentially means what I have already mentioned before, which is that to build an agentic system and to put it in production, the single most important thing that you're going to have to add is a very reliable tracing and monitoring system. Okay, so you need a very clear observability platform to make sure that your agents actually are making sense. As they say right here, adding full production tracing lets us diagnose why agents failed and fix issues systematically. Beyond standard observability, we monitor agents' decisions, patterns, and interaction structures, and they do say that they do not read your actual messages while doing this. All right, but the important part right here is the first part, the first part that I mentioned. Having this observability system that allows you to see exactly where an agent went wrong is incredibly useful, and not only useful, like it is mandatory if you want to create these kind of systems. Also, we see right here that the deployment needs careful coordination because precisely there is a big problem with these kind of updates because the processes take a long time to complete. And this is what you see right here. Agent systems are highly stateful webs of prompts, tools, and execution logic that run almost continuously. So you may have a process running for 15 minutes. So if you push an update during that time, that is going to break something. So what they did is they use rainbow deployments to avoid disrupting running agents by gradually shifting traffic from old to new versions while keeping both running simultaneously. Very, very interesting. Then we see that synchronous execution creates bottlenecks. This is more of a to-do list for them. So what they say is that currently, as we have mentioned before, there's a lot of parallelism going on in their approach. You have the master agent delegating to sub-agents, and all of these performing tasks concurrently, and then each one of these is going to perform tasks with their own tools concurrently. But if this guy right here finishes and then brings back their resulting of their research like 2 minutes in after the research started, if this guy takes 15 minutes, this guy will not get additional instructions, right? This guy will stand there sitting, waiting for all these other guys to finish before receiving new instruction. And that kind of creates a bottleneck. That's what they have to say is right here. Even though they are already doing some pretty accurate and pretty sophisticated parallelism, okay? So there we go. That is what we have seen with production systems. And in conclusion, let's just close this by saying, by reading this paragraph right here, they say, when building AI agents, the last mile often becomes most of the journey, just like in regular software applications. Code bases that work on developer machines require significant engineering to become reliable in production systems. Of course, this is true also for any kind of software, but for agents, it's even more clear because there are just so many more things that could go wrong. The compound nature of errors in agentic systems means that minor issues for traditional software can derail agents entirely. One step failing can cause agents to explore entirely different trajectories, leading to unpredictable outcomes. For all the reasons described, the gap between prototype and production is often wider than anticipated. And that, of course, makes a lot of sense. But I'm very happy to see that agentic systems are actually becoming more and more common and that we're seeing more people actually put them in production. I am very happy to see where this is going, and I am very excited to also hear what you guys are building. So I hope that you enjoyed this kind of video. This was kind of a different approach to the videos that I usually do. Don't worry, I will continue doing tutorials, of course. That's what I like the most. But let me know if you want to see more videos where I just go over one of the papers or one of the latest articles by some Anthropic or OpenAI and just explain it and summarize it for you, okay? So it's been a pleasure as usual, and take care. I will see you next time.